Hey guys, it's me, Lorenzo, and today's video is on the equilibrium constant.
So we would like to quantify equilibrium systems and the relative concentrations of their constituents. So let's have a look at this system here. This is just a theoretical system where these two reactants A and B make products C and D. Let's introduce the idea of a reaction quotient. We use that letter Q here, and it'll be the ratio of products to reactants. That quotient will be from 0 to 1 to infinity, and of course if it's from 0 to 1, you'd imagine the reactants were favored, and from 1 to infinity you'd think that the products were favored. If we put little coefficients small a, b, c, d on there, then the reaction quotient will have this form. Here, where we've got the large letters being the items in question, the square brackets, the concentrations, and the little letters there, the coefficients, are now being used as exponents. So we just use concentrations. Gas pressures are okay in an all gas system, but we'll use concentrations only. So just concentrations, and this is the shape of that thing we're calling the reaction quotient, products over reactants. Let's write the equilibrium expression for this reaction here after just checking which things are in. Aqueous solutes and gases have concentrations, solids don't. Of course, liquids only if there's more than two of them. You can see here the reaction quotient just has the nitrogen monoxide concentration squared. Okay, notice then, if at a certain temperature the system is at equilibrium, then we'll give this Q a special, this Q value a special name called KQ, and it's a characteristic of the system at that temperature as you wrote it down. You'll sometimes see KQ called Kc if it's done with concentrations, or Kp if it's done with gas pressures, but we'll use Kc exclusively in Chem 12, and Kp will show up in AP chemistry. So just as an example here, let's find Kc for this system. We'll write the Kq expression. The ammonia concentration needs to be squared, see the 2 there, and the hydrogen concentration needs to be cubed, see the cube in it. The square brackets mean concentration. Now with round brackets, we'll put the actual values in, and these come from the problem as stated. Then we get this value of 3.8 by 10 to the 4. Remember, round brackets are values, square brackets are concentrations. So this Kq value here has no useful units to our purpose right now. It does have units, but we're just going to leave those alone for now. Anyway, it's a numerical value, experimentally determined for a reaction at a given temperature. That's the KEQ. And it's equal to the equilibrium expression for that reaction at that temperature. This suggests we can calculate values given other values and predict what will happen in the future and look back to the past. So that really gets interesting. And try to get comfortable with this idea of the equilibrium constant, and it forms an important foundation for much of what's coming next. What is coming next? Well, after you have a look at these next two videos, stay tuned for our next lesson, Lesson 10, Equilibrium Calculations, Part 1.
This is my dad's YouTube channel. It's awesome. So like,